Now the last one, and that is abelian group. So who are the sets who can be an abelian? Let's see our so abelian are those which will satisfy commutative property. Okay, and once someone reaches up to commutative property, almost rarest rare is someone who will not be this. Almost the one who satisfy all these four property definitely becomes out to be abelian, because commutative is very simple property which is satisfied. Let's see what that property is. Okay, commutative property. What it says, a set with respect to any operator is to be satisfied commutative for all the elements of A. There is an element such that when we operate in such a way, A operated with B or B operated with A, the result is same. Very simple property, and those people prove out to be abelian. Now we were proving this with respect to addition, I guess. Okay, integers with respect to addition. Let's see, what does it make a difference for integer to be 1 plus 2? Definitely is always going to be 2 plus 1. It is some kind of associative. Okay, only the associative have a different set of operation, different way, and this is elements, the order is different. And definitely who satisfy up to the four properties, most probably all the people will satisfy the commutative property. So definitely integer with respect to addition satisfies commutative property, and they are now a abelian group. And the only one who prove out to be abelian is this. Okay, but we also have to remember that multiplication with integer were monoids, natural number with multiplication were also monoids, natural number with addition were semi-groups. So these are the things that we have to remember. Sometimes it will be given that there is a set who is a group or who is abelian, and we'll ask you to cross out different answers. So you have to know that if someone is abelian, that means he is satisfying all the 5 properties. So now these things for all the rest groups, this is a group of real numbers. Then, for example, you will be given a set of even numbers, odd numbers, matrix, set of matrix. And all the elements of the set is nothing but a matrix. So what operation? Matrix with respect to addition, matrix with respect to subtraction, multiplication, division, this kind of. Now let's see if we are able to guess for real numbers. Real number with respect to addition. The real number, if natural number and integers were able to prove, then definitely real numbers with respect to addition is going to be a part of algebraic structure. Easy to guess. What about semi-group? Definitely they will be semi-group, because for semi-group they have to satisfy what property? Associative, and doesn't matter for. What about monoids? Whether they have identity? Yes, for addition 0 is required, they have that, right? Now you can guess the property with likewise also whether they can be a group, because group require is the inverse element, so they will be having all the inverse with them, right? Real number have everyone. So, and whether they are abelians, commutative property is definitely satisfied, doesn't matter for the order. Subtraction, yeah, now the thing is real number with subtraction, yes, they will be algebraic structure, because doesn't for them the result will always be in the resultant element should be a part of set, right? So integers, the result always is a part of set, because even the result is negations, real number have them. What about real number with to be a semi-group? They should satisfy what? No, they will not.
Associative law.
Associative, they can't be. Subtraction itself is not an associative operator. Monoid, monoids, they
No.
the identity element is, but no need to check only because things are
Yes.
like didn't pass to form this. Okay. Multiplication, yes, multiplication. The result will always be there. The real numbers. I hope multiplication also will satisfy association, no problem for them, and they will also satisfy have the identity elements. One is there. Inverse property, that is to be a group, right? Inverse property. So what is the inverse property? For inverse property, the inverse elements should be present in the set, and we know that in real number set all the elements are there. If we think of negative elements, or all the positive negative elements, the the fractions are there, so we by default assume that real number can be a group because every element will have its inverse present in the set, right? In real number set, because it has a lot of elements already there. But we should not forget one thing: real number also has one element, and that is what? 0. What about this element? So inverse property. So what this property says, that every element should have a inverse element. Whether zero's inverse element is present in this set, what this property says, that for a 0 with respect to multiplication, which number I should multiply with 0 to get the identity element, and the identity element for multiplication is what? 1. So which number I should multiply with 0 so I could get 1 as the identity element, and that is not possible, right? There is no such element that we will get here result as 1. And that is the reason that 0 is one and only one element which does not have its inverse in real number set. And because of this one element, multiplication, real numbers with respect to multiplication fails to satisfy the inverse property, and that's why they are not groups. Okay, so they are not groups. And then they can't be abelian also, right?
Now real number with division. Again, to be a algebraic structure, they should satisfy the closure property. That means any real number divided by real number should generate a real number. And we think that as it has all the set of fractions, non-fractions, so it will clear out this property. But don't forget that it also have 0. And any real number divided by 0 will not generate a real number or any number. It's just a mathematical exception. So keep it in mind, real number with division fails the closure property, and that's why they are not an algebraic structure. And none other.
Now talking about matrix, right? What about matrix? Matrix with respect to addition. So whether are they algebraic structure? So for to be algebraic structure, they should be satisfying the closure property. And for multiplication, what the closure property says, that if I add 2, this is a set of matrix, right? That means matrix which has all the elements as a the set has all the elements, that is matrix. So this is a set of matrix, and if I add 2 elements of matrix, I should get is the resultant element also as matrix. As this is a set of matrix, if I will take any 2 elements to perform the addition, whether the resultant element is a matrix? Yes, it is, because addition of 2 matrix will always be assuming the order is same, okay? Assuming the order of the matrix are same. So definitely we will get a resultant matrix as a matrix, which is nothing but a part of set also. That's why matrices now here satisfy the closure property, and thus they are an algebraic structure. Right? They form an algebraic structure. Now the next property, that is associative. Associative property to be a semi-group. Okay, whether there makes any changes to associate in a different way, because here I am just changing the association, not the order. Order is same, M1, M2, M3, but the association is different. M1 is first added with M2 and then added with M3, and here M2 is added with M3 and then added back with M1. Whether this is going to make a change? No. The result is going to be same for matrix. And that's why, because of this, again, associative properties satisfy, and that's why matrix are forming to be a semi-group. Semi-group. Now, what about the next property? That is for forming a monoid. And for monoid, there should be an identity element in this matrix. That means an element. So if any matrix we add with its identity element, we should get back is the matrix. So for addition, we can have a identity matrix, right? There are identity matrix. We can have 0, 0 for, right? This matrix we can take as identity matrix, and yes, the result of this addition will be the matrix itself. And that's why with this also, matrix satisfies the identity property and hence successfully forms monoids. Right? We're talking about the next property, that is the inverse property to be a group. So what about this inverse property? Inverse property says that the inverse of every matrix should be present in the set. Right? And for this particular thing, matrix adding with its inverse, we very well know if I want to add a matrix, its inverse, that is, I can change the magnitude of the matrix, and when I do so, the resultant element is nothing but the identity I will get. That is, for addition, I will get 0 if I perform the addition of matrix with its inverse, that is, with negative magnitude. And yes, hence because of this also, the addition property with the addition operation with respect to matrix, okay, successfully satisfies the property, that is the inverse property, and hence they are what? They successfully forms a group. Groups. And what about the next? The next and the last property, that is the commutative property. What this commutative property says that if I add a matrix with another, and rather I add this matrix with the first, whether the order is going to make a difference. Yes, there is a difference. Now this is the difference between the matrix addition and multiplication. Okay, so this is what the thing is. So if I add two matrices in this order, whether it is going to make a difference, no issue. For matrix also I can perform, and the addition will be same for this matrix. So they also satisfy commutative property, and that's why they are abelians. They form to be a abelian group. Right? Let's discuss about matrix with multiplication also. Okay, so matrix with multiplication. Simply let's go on doing this. What about matrix with multiplication? So the first property, that is the closure property. So if I multiply one matrix with another matrix, what would be the resultant matrix? Definitely it will be a matrix only. And that means it satisfies the closure property, and hence they are an abelian structure. Sorry, algebraic structure. Right? Second property, that is for association. So if I multiply two matrices, three matrices in this way, does it going to make a difference with the result as different association? So here I am not changing the order of the matrix, but rather the association, right? First I am multiplying these two, and then multiplying with the third matrix, multiplying m2, m3, and then the first matrix. Does the result is going to make a difference? No, for multiplication it's going to be same, and it is going to satisfy the associative property, and that's why they are semi-groups. And the next property, that is for monoids, that requires identity property. So identity, so there is an identity matrix, right? For multiplication, we can take is we have identity matrix that is diagonally having a right. You can take this matrix here, and using this identity matrix, whether I am going to get the same result? Yes. So the multiplication of this with respect to this matrix with the same order, definitely. I have just taken an example. So it will satisfy the identity property, and hence they are successfully forming to be a what? To be a monoid. Monoids. And then the next, that is the inverse property. Now again the inverse property, and what the inverse property says that when you will, with respect to multiplication, when you will multiply two matrices, the result should be, sorry, it's inverse of this matrix, that is which matrix I should multiply with m1, that I should back get a identity matrix. Okay, so which such element, and we very well know that we can take the inverse of any matrix, right? So taking the inverse of whatever matrix we are dealing, okay, we can deal that, and then we have inverse. So the set of matrix, Okay, so if we say this is the set of matrix, they will also have inverse matrix also, right? Their inverse also. But the thing here again is there will be a problem, because when we take the inverse of some matrix, we also divide the matrix with uh, a determinant, right? If you again go through the process of taking the inverse of some matrix, we have to divide with determinant also in that process. And if in case the determinant by some reason comes out to be zero, it could be possible. If it comes out to be zero, then again it will arise a error that dividing any element with zero again can generate a no number in, right? So then for due to this reason, matrix will fail to prove out to the inverse property, right? So we will not get in that case any identity matrix. So this is one of the possibility, and that is the reason because of that the um, divide by zero thing, we are not able to conclude that matrix will satisfy this inverse property, and that's why they are not groups. So matrix with multiplication only are up to monoid, right?
So this is all about group theory. Next lecture we'll see examples.